Okay, hi, welcome back everybody. So last time, where did we stop? We were talking about the function field analog of the problem of counting square-free integers in a box. And we had defined, so I'll just recall, we had this function square-free sub q of n equals number of monic square-free polynomials in fq brackets t of degree n, and I had discussed but not proved the fact that just as in the number field case, this guy had a limit, or an asymptotic behavior, if I take the limit as n goes to infinity of q to the minus n sf sub q of n, so this quantity, the limitend being the probability of square freeness of a random polynomial, this limit exists and is equal to 1 minus 1 over q. And I think Chantal is going to tell us later about why this must be true from the viewpoint of L functions. So I said I didn't prove this. I actually am going to prove it, or at least sort of show you how a proof works. And I'm actually going to prove that in this case, something much stronger than this is true. So let me say what I mean, and we'll sort of start from there. So in fact, I'm going to say the same thing, but without the limit. That the number of square-free polynomials is equal to q to the n times 1 minus 1 over q on the nose, with no error term whatever. So not plus a little of anything, but just simply is equal. But now I have to be careful because what I said is not quite true. For instance, linear polynomials, of which there are q, have an annoying habit of being square-free, because their degree is so small that they can't possibly be multiple of any square. So this is clearly not true for n equals 1, but it is true for all n bigger than 1. Once you get to degree 2, where it's even possible to not be square-free, this kicks in and it's true on the nose. So let me sort of give a sketch of an argument for why this is true, because I feel like I should prove something. So proof, let me denote by sigma sub ne the set of monic polynomials degree n of the form. So I'm going to factor it into a square-free part and a square part. I mean, any polynomial can be factored in this way, so I'm going to say it's a of t times b squared of t with a square-free b of degree e. So the point is that any polynomial whatever can be expressed in this form, can be written as sort of a square-free part, basically all the irreducible factors that appear to an odd degree, you take one of each, times some square of whatever degree, and there's q to the n polynomials in all, so all q to the n polys can be factored, and indeed can be factored uniquely in this way. So what that means is that q to the n is the sum from e equals 1. I could say e equals 1 to infinity, because when e is bigger than n over 2, this is just 0, but let me write, I think the ceiling of n over 2 is right, times the size of sigma ne. So I'm just taking the set of all monic polynomials of degree n and partitioning them by what's the degree of the largest square factor. But as you know, so this is some kind of piece of elementary combinatorics. If I have a formula for the successive sums of a thing, then I can get a formula for the thing, essentially by telescoping. So if you like, it now immediately follows that no, I don't think so. Should we vote? So remember, I banished non-monic polynomials in the first lecture. They will never be mentioned again. Yes. That should be. And that's important, actually, because what are we actually trying to compute? Lest we forget. The what? Oh, that I don't know. I mean, that's still literally true. So the point, but the point being that to know that what we're looking for is the size of sigma n 0, but it's clear that the size of sigma n e, after all, there's no relation between A and B, so it's just counting how many square free guys there are, possibilities for A. A is degree n minus 2e, and then B can be whatever it wants among its q to the e choices. So you have this times the value of our mystery function at n minus 2e, and then it's an easy induction to compute the value of sfq of n from this. You plug this into, I guess, well, you can see my point. You plug this into here, and then by induction, you actually need two base cases. So starting from sfq of 0 equals 1, and sfq of 1 equals q, you get the desired result. Actually, one thing I find rather charming about this induction is it's an induction where you need two base cases for both of which the stated theorem is actually false. But then it starts being true at 2, as you can easily check from this, and then it's true thereon. So that's just a piece of combinatorics. So as I said, you now saw from Bjorn a pretty easy proof of the claimed asymptotic in the case of Q. You've now seen from me an easier still proof of the asymptotic and even an exact formula in the case of FQ brackets T, and yet I'm still completely devoted to giving you a much harder proof of this fact, which I will embark on now, which is more geometric. But as a sneak preview, in case this looks super easy, I'll just comment that this is actually the motivic proof. Does that make it sound harder? So I'll circle back and sort of have a remark about what I mean by that later on. But I just have to feel like I'm doing something other than doing induction and adding numbers together. Okay. So let me begin. Actually, this is a good moment for an aside. I think I'm going to actually really talk quite little about general function fields, although it's an important subject. I'm going to sort of stick to FQ parentheses T, but let me just remark that the absence of an error term, which is quite striking, the fact that we have an exact formula, I think it's kind of misleading. And so for a general function field, FQ parentheses C, will indeed have, so I think I'm not going to sort of say there's, in the notes I sort of explain this at more length and like talk about divisors and effective divisors for those of you who don't ordinarily think about those things. I think I will just assert that I'll just say the natural analog, which one might call square free sub C, of what shall I call it, of n, is it's still the zeta function of C evaluated at 2 minus 1 times q to the n, but just as in the case of number fields, there is an error term with some power saving size. So loosely speaking, for those of you who think about curves over finite fields, what's going on is that there's a contribution from the cohomology, the h1 of the curve. In the case where the curve is a p1, there's no cohomology there, so there's nothing going on. but in the case of a general curve, there is. So actually, the error term for this was worked out in great detail by Byung-Chul Cha in a paper of 2011, and I just wanted to mention this because actually he and I were in the same student group with Spiro at the very first Arizona Winter School, so I was pleased to see his name come up when I was researching the notes for this talk. I was like, I remember that guy was in my group. And that's the experience you guys are all going to be having for the rest of your life. Okay, so what's the moral lesson of this slide? And I really want to make this point quite strongly, that the analogy is between number fields and function fields. It's easy because I'm going to talk mostly about Q and about the rational function field FQ parentheses T. It might seem like I'm sort of saying that there's analogies specifically between Q, the so to speak bottommost number field, and FQ parentheses T, which you might think of as the bottommost function field. But I want to kind of resist that. It's more like it's not so much that there's any particular number field which is an analogy with any particular function field. I think that can be rather misleading, as we see here. Rather, you should more just think that sort of all global fields are alike in some important sense. So I used to sort of say all global fields are alike, but every local field is local in its own way, to paraphrase Tolstoy. But now it seems like Schulze has proved that all the local fields are alike too. So I don't have anything to say anymore. So okay, end of excursus about general function fields, and from now on I think it's going to be rational function fields all the way to the end. So now is where we're going to start moving towards what I would consider truly geometric. So here's a question: how do you tell? Oh, this is sort of in the right place? Okay. How do you tell whether an integer slash polynomial is square free? I mean, obviously one way is to factor it and sort of see what the factors are. And in the case of integers, it's actually a very interesting industry about that's a pretty expensive way to try to check whether an integer is square free. It turns out that there are faster ways, although nothing so good as polynomial time. But for polynomials, there's actually a much easier way. Namely, we can compute the discriminant. So let me explain what goes on with that now. I'll give you an example, the example of cubics, where I can actually write stuff down. So Z, somewhat hard. FQ, and actually there's nothing special about finite fields here, so maybe I'll just write K brackets T, polynomials over whatever field. So compute discriminant. Let me explain what that means. If I have a polynomial so I'll use cubics as an example. Let's say T cubed plus A1 T squared plus A2 T plus A3. And I think I will write one out, just so you see it. This polynomial is square free if and only if the following expression, A2 squared, A1 squared minus 4, A3, A1 cubed minus 4, A2 cubed plus 18, A3, A2, A1 minus 27, A3 squared is not equal to 0. That seems kind of crazy, but there it is. So there's this completely algebraic criterion in terms of the coefficients for whether or not the polynomial has square free. It's not this polynomial and the coefficients can see something about the factorization of the polynomial. Why should this be so? So this is a very beautiful exercise from Galois theory, which I will explain. Where would one get such a thing? The idea is this. So in fact, this is delta of P. That's my name for this quantity, the discriminant. And by definition, it's the product over all I not equal to j of theta I minus theta j, where the theta I are the roots of P. So this is a product of, n squared minus n things. And what we can see, let me slide up a little bit. What I can see about this expression is that it's evidently a polynomial in the roots, which is fixed by permuting the roots. And that means that it has to be a polynomial in the coefficients, which are the elementary symmetric polynomials in the roots. So since this is preserved by Sn action on roots, it is a polynomial in the AI. And if you do this for a cubic polynomial, you will see that you get exactly this sort of somewhat, I mean, it might not be a simple polynomial, but you'll see that you get exactly the polynomial that I wrote down. And what this allows us to talk about is what one might slightly pretentiously call the moduli space of square-free polynomials. So what do I mean by that? This is the open subvariety of affine n space. So if I'm going to talk about affine n space, I need to give it some coordinates, and my coordinates are going to be called to remind you that you're supposed to think of them as coefficients of a polynomial. I'm going to denote by my coordinates by a1 through an. And by the way, just to like add to the pretentiousness factor of this piece of paper, I could call this affine space, instead of calling it affine space, I could call it the moduli space of monic degree n, of all monic degree n polynomials, square free or not. And I just mean that its points parameterize the polynomial. So if I have a point on that space, it gives me coefficients, that gives me a polynomial. I mean, for those of you who like representing functors and who doesn't, every time I say moduli space, whatever functor you imagine being represented is being represented, but I'm not going to need to adopt that point of view for these talks. Anyway, so what open subvariety of affine space is it? I mean, what an open subvariety is precisely the locus where some polynomial or set of polynomials doesn't vanish. And so indeed, it's just open subvariety where delta, which is a polynomial in these coefficients, in other words, it is a function on this affine space, does not vanish. I got to give this thing a name because I'm going to talk about it a lot. So we'll denote this space conf n. So now I got to explain why I call it conf n. Maybe it's easiest to think of what's going on over the complex numbers. So in general, so conf n k is the set of square-free monic polys of degree n with coefficients in k. And in a minute, we're going to spend some time talking about the complex points of this space. So we started out talking about the FQ points. So I'll just remark that this function SFQ of n is none other than the number of square-free polynomials over FQ, which is to say it's the number of FQ rational points on this variety, whatever it may be. But we're actually going to take a turn away from thinking of this variety as a variety over a finite field, and instead, I mean, it makes perfect sense for any field. So look, we're going to think about it over the complex numbers. So it turns out that over the complex numbers, this is the same as the set of unordered, and this is important, n tuples of distinct complex numbers. Actually, I'll underline both, because both of these words are important. And And what is this isomorphism? Well, it's simply, I send a polynomial. See, what's nice about C is that it's algebraically closed. And so if I have a polynomial, a complex polynomial, it has roots. I mean, it factors into linear factors. So P goes to the set of roots of P, and the condition that P be square free is precisely the condition that the roots be distinct. And of course, this is a bijection because I can go backwards. If I give you like n complex numbers in a bag, which I'm allowed to shake up, and all I know is that they're all different, you can multiply together like t minus z1 and up to t minus zn and get a square free polynomial. And it's easy to check that because everything is monic, that's a bijection, and a polynomial is uniquely determined by its set of roots. So the reason this is called, the conf is short for configuration, and the reason this is called configuration space is because we think of it as a moduli space for configurations of endpoints. That's just kind of a term of art for endpoints that are required to be distinct. So, so another way to say it is conf n equals configuration space of n points on C. So we started with one question, the question of counting square frees in Z. We introduced another question, the question of counting square free polynomials over a finite field. Now we have another way of thinking about the set of square free polynomials, but it's somehow, the finite field has been left behind, replaced by the complex numbers, and there's no apparent counting problem to be done at all. So where do we become geometric? Conf NC, conf n of FQ is just a set, right? What can you do with a set? Count it. There's like nothing else you can do. You just have to sort of sit glumly and stare at it and count its elements. Conf n of C, the configuration space of n complex points, is a space. It's a manifold. If you like, it's a complex variety, but I think for what I'm going to say now, I'm just going to think of it as a manifold, as a topological space. So we can do much more than count it. We also can't count it, so that's another reason not to do that. So we want to study the geometry of this space, and as I'll explain later in this morning's lecture, and as some of you know, there is a deep, deep relationship between the geometry of the complex points of a space and the numbers of its points over FQ. So let me start thinking about the geometry of this space, and now is where we sort of start to get into the zone that we might truly call geometric. So conf NC is a manifold. What can we say about its geometry? Well, let's start small. I always say start with the easiest problem. So conf 1 is just a configuration space of one point on C, so that's C. Okay, good. It's a plane. Homotopically speaking, it's a point. It's a contractible space, so not so much to say there. Already things get interesting with conf 2, and in the course notes I have a rather detailed description of conf 2. I think I'm going to sort of slightly elide that and sort of draw a picture to kind of show you what it is in a way that I hope you'll find believable. So it's the space of unordered distinct points. So maybe we are going to talk, in order to say this fast, I'm slightly going ahead of introducing something I'll talk about later, but the space of ordered pairs of distinct points maps to this. Namely, if I have an ordered pair of distinct points, I can just forget the ordering. And the space of ordered pairs of distinct points is kind of easy to understand topologically because the first point is here. You choose it anywhere in C, but because C is contractible, we got to kind of be topologists about this. Choosing a point in a contractible space is like not making a choice at all. Do you guys buy that? Okay. So having made that choice, though, now we have an interesting choice for Z2 because it can't be Z1. It's taking when it sort of wakes up in the morning and decides where to live, it has to live somewhere on the complex plane apart from Z1, and that's the complex plane with a point removed, which homotopically speaking is a circle. So Z2 is somewhere out here. So Z1 is chosen from C, Z2 is chosen from C minus Z1. If I were to be more precise about this, I would say this space has a fibration, it maps to C, and the fibers are homotopic to circles. And so in the end, you should think of this space as a circle. Basically, the choice of Z1 doesn't matter, and then Z2 is chosen from a space that looks like a circle. And what happens is that the forgetting the ordering ends up on the level of the circle being the antipodal map. So you're modding out the circle by 180-degree rotation, and that quotient is just a smaller circle that's like half as long. So this is a circle. And again, in the notes, I give a very explicit algebraic description of the map to the circle for those who are not convinced by my picture. Okay, so we did 1 and 2, but there's a lot of other ends besides that. So as n grows, conf n gets more complicated. It's not completely obvious, by the way. I mean, after all, I could also say, oh, maybe affine n space gets more complicated as n grows. But from the point of view of topology, or at least homotopy theory, it really doesn't. It's just like, it's still always contractible. So let me justify my claim that this space actually does get more complicated as n grows. One natural invariant of a topological space that we might want to think of as this fundamental group, right? That's kind of one kind of very hands-on thing we can ask about a topological space to sort of understand what's going on with it. So e.g., the fundamental group pi 1 of comp n, and once again, let me sort of draw a picture of this to indicate what it is. This would be a good place to kind of have like a movie. Let me draw a picture of a loop in comp 4. Okay, this, as I'm sure you can see, is the complex plane with 4 points on it. So that's a configuration of 4 points. A loop in comp 4 is a way of moving around in configuration space, starting from here and then coming back again to here at the end. So let me draw the end of the loop up here, and I'll try to draw the same 4 points. And now what I want you to imagine as I draw my loop is I'm going to kind of move upwards along the page, and it's like a little animation of those points, like moving around. So here we go. This point is like moving around somewhere, blah, 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 blah. And it doesn't have to come back to where it started, right? Because all I know is that I get the same configuration of 4 points, but they don't have to be in the same order because it's an unordered configuration. And then this guy is moving around too, and it's moving around pretty freely, but the one thing is it's never allowed to occupy the same position as one of the other points. 2 points can never meet because you have to, then you would be outside configuration space. So when I sort of draw this little thing, it either has to like go behind or go in front. So maybe I'll draw it going behind because I can't erase this permanent marker. And then I've given myself a drawing challenge here. Maybe this guy goes here, and then this guy kind of maybe stays over here. And of course, what this is this is a picture of a braid. And composition of 2 loops just corresponds to stacking 2 of these diagrams atop each other. And so, in the end, the fundamental group of this space is the Artin braid group on n strands. And from group theory, we know that this is like a very big, rich, complicated group that just gets bigger and bigger as n grows. And so this is sort of my argument that these spaces are sort of somehow pretty impressively big and interesting as n grows. So because of that, that's all the more reason why I think this result of Vladimir Arnold from the 70s is quite startling. So here it is. So theorem, Arnold, for all n bigger than 1, H naught of this configuration space with rational coefficients is Q. Oh, so by the way, things are going to get kind of cohomological in here for the next, for the rest of today's lecture. So some of you guys dig cohomology and some don't. I want you to. It's part of my goal to sort of say that cohomology is part of arithmetic statistics. So I'll sort of say as I go, the H upper naught you can think of as measuring the connected components. And actually, my entire third lecture is going to be about H naught. So if I can't get you to like cohomology, at least I can get you to like H0. So you should think of this as being the connected components, and so that's saying something that is somehow not so amazing, which is that the configuration space is connected. Even this, like, you should actually think about it for a second and be like, oh yeah, I can get from any n points to any other n points, essentially because a two-dimensional space like the complex numbers is sort of big enough for points to kind of get past each other without getting stuck. But that is true and easy to prove. The H1 of this space is also just one-dimensional. That you could check, for instance, the H1 of a space can be computed by computing the abelianization of its fundamental group, and you might, if you know something about the Bay group, you know that it has a well-known presentation, and you could compute its abelianization from that, for instance. So that also, maybe you wouldn't be so amazed by. There's like lots of like big groups that have small abelianizations, but then what's really amazing is that, now what about the higher cohomology? That's 0. There's nothing else. So for all I bigger than 1. So what is this saying? If somebody kind of came up to you in a dark alley and said, I'm thinking of a manifold, and its H0 is one-dimensional, and its H1 is one-dimensional, and has no other cohomology, and I'll kill you if you don't tell me what it is, you would say a circle, right? So that's sort of what you're supposed to think when you see this. What Arnold is telling you is that all of the spaces, you know, first it's a point, then it's a circle, then it's something more complicated, then it's something more complicated, then it's something more complicated. Through the lens of cohomology with rational coefficients, the story is totally different. First it's a point, then it's a circle when n is 2, then it's a circle, then it's a circle, then it's a circle. It's always a circle. I mean, that's quite remarkable. And by the way, I should say that with integral coefficients, the story is completely different, and there's much more cohomology, and it's a very interesting story, sort of that goes deep into topology, which I'm not going to tell. But for reasons that you'll see, for this series of lectures, we care only about the cohomology with rational coefficients, where the behavior is much more tame. So this is an example, again, sort of a sort of spur down a highway that I won't take. This is an example of the phenomenon of homological stability, which is an absolutely huge area in contemporary algebraic topology. This theorem is kind of just about where it starts, like work of Arnold and work of Graham-Segall in the 70s. Loosely speaking, what it means is that if somebody comes up to you and says, what's the rational homology of configuration space? You don't have to ask which configuration space. It's stable. That's what's, and similarly, I mean, so this is an example of stable cohomology. And I'll just say sort of the most famous example of this for the people in the room who like algebraic geometry is that the moduli space of curves is the same phenomenon. If somebody asks you what's the H5 of the moduli space of curves, you don't have to ask which genus, because for genus large enough, it's always the same. So a very similar kind of phenomenon. And in some sense, oh, sorry to cover that up. In some sense, sort of for the same reason. That goes farther into topology than I want to go in this talk. So the claim I want to make is that this theorem of Arnold, somehow, once again, this is the same answer as the answer I got for counting square-free polynomials over FQ and counting square-free integers. And to explain what I mean by that, because once again, cosmetically, it looks very different. This is where I will talk about Grothendieck-Lefschetz trace formula, and then I think I'll be able to say a little bit better, like what I think we should mean by geometric analytic number theory. Okay. Because it seems I've gotten far away from counting, right? But not so far. So that was the sort of complex manifold story of the cohomology configuration spaces. We're still doing cohomology of configuration spaces, but now I want to tell the Étale cohomology story. So this part of the talk always presents kind of a expository conundrum, because some of you are familiar with this machinery and some of you are not. If you're not, I sort of can't do enough to kind of make you guys experts in it in like a short lecture or a short lecture series. So I want to try to black box it as much as I can, and you guys can tell me if I'm successful. I want to kind of tell you exactly as much about Étale cohomology as you need to know in order to sort of follow through on the main ideas. And again, I will comment that there's going to be a whole lecture this afternoon where we only care about the H0. So even if you don't like all the Étale cohomology, I hope I can at least make you like the H0. So let me start with the Grothendieck-Leshitz trace formula. And then we'll sort of stare at it and sort of talk about what the pieces of it mean. It says the following: it's a formula for the number of points on a variety over a finite field. And here's what it says. So if I want to count points on a variety over a finite field, I can express it as a sum over I. It's an alternating sum of the following gadget. And then I'll sort of stand away from the slide projector and say a little bit about what I mean by this. Okay, I think I've said everything I need to say. Okay, so what does this mean? That thing, oh, it's not, so am I literally going to be prevented by the, okay, can you guys remember that's the number of points on the, I thought my thing was as wide as my paper, but I guess now that I've tested it, I see that it's not. Let's start from the far right. That thing on the far right looks like a cohomology group, and indeed it is, but in this cohomology theory, Étale cohomology developed by Grothendieck and his successors, and all I want you to know about it is that just like any cohomology theory, it's a vector space that you assign in a canonical and functorial way to a space, in this case a scheme or a variety over the finite field. This QL is the coefficient ring. It turns out that you can't make a good Étale cohomology theory with Q coefficients, as much as you might like to. So this is a small expedient where once I'm talking about Étale cohomology, my vector spaces are all going to be over QL for some L-adic field QL. And it's not going to matter which one. So you shouldn't worry too much about the L. And the main thing I want you to know about this is that this cohomology group, unlike a sort of usual topological cohomology group for a complex manifold, it's actually a representation. It carries an action of a group, namely it carries the action of the Galois group of FQ over Q. In fact, more generally, and I'll sort of mention this later, for a variety over a field, you can always get an action of the Galois group of that field, but since we're now talking about varieties over a finite field, the action is of, so maybe I'll even sort of, I hate to pollute my beautiful formula by drawing this, but I'll just remark that this vector space carries an action of gal FQ bar over FQ. But this is, of course, the nice thing about finite fields is that their Galois groups are cyclic, or pro-cyclic, if I'm to be completely accurate. They're topologically generated by the Frobenius operator, which raises every number to the qth power. And so what I'm doing is if I have a representation of that cyclic group, then Frobenius acts on that space, and an operator on a finite dimensional vector space has a trace, and that trace is a number, and that number is what I'm taking alternating sums of. And of course, part of the miracle of the theory is that that number is actually going to be not some crazy L-adic transcendental, but like an actual algebraic number. That's quite remarkable. So this probably looks like if somebody kind of came and handed this to you, you might not feel you were any closer to having a formula for the number of FQ rational points on some variety that you might be interested in. But now let me tell you the following thing. I mean, I say that this is some cohomology theory, and there's lots of different cohomology theories, but this one, in some sense, is not so far from topology in the following sense. So, So now I'm going to have to say some things in a somewhat vague way. So the EGA types among you will have to kind of settle down when I say some things vaguely, because I think it's necessary at this point. So when X is a variety that, so to speak, makes sense over both the complex numbers and the finite field. So maybe I'll say for the spec fans, I'm thinking of let's say a variety over spec Z or something like this, subject to suitable conditions. We may hope that these two cohomology theories have something in common. So maybe you say, on the one hand, you compute this mysterious thing, this atal cohomology group, and maybe for the length of this slide, I'll have X be compact, so I don't have to write compactly supported. And this just means if I take the complex points of that variety, it's just going to be a good old complex manifold whose topology I can compute whose cohomology I can compute in the usual topological sense. And then I might hope these are the same. But now, wait, what do I mean? One of these guys is a rational vector space, and one is a QL vector space, so I can't literally mean that they're the same. And this guy has an action of a group, which this guy does not. So maybe let me just sort of say something quite modest. Let me say maybe one hopes that the dimensions are the same. That at least clearly makes sense, right? So that's a thing that we can ask for. And we're going to see that in many cases of interest, this is indeed true, so that the computation of the dimensions of the spaces on the étal side can be replaced with the computation of dimensions of cohomology groups on the topological side. Okay, so far so good. Of course, there's also the issue that in order to use this formula I've got over there, I not only have to tell you the dimension of the étal HI, I have to tell you how this Frobenius operator acts on it. That's a challenge too. Still, let's see how this plays out in the case that we've discussed. So maybe I'll say, under good circumstances, again being vague, this is so, and now with no justification whatever, but I'm happy to talk about it later, behind closed doors, I will say that the situation of the configuration space, which is certainly a variety that makes sense over FQ and makes sense over the complex numbers, again, it's a scheme over spec Z for those who like this, it does indeed satisfy those favorable circumstances in which we can compare. And so what is the analog of Arnold's theorem is again true in the case of comp n. We indeed have, so here's a fact, for all n bigger than 2, H naught étal comp n over FQ bar QL equals QL. H1, so I'm not going to write this same thing every time, but you should understand that that's what's after the H1. Yeah, John. Oh, is it not? Oh, this thing I'm writing is not visible. Good, okay. Equals QL, and the HI equals 0 for all I bigger than 1. But now I got to say one more thing, because when I talk about Frobenius, so moreover, Frob acts as one on the H naught étal and as Q on the H1 étal. So on the two non-zero spaces, I can tell you exactly how Frobenius acts. And essentially that's because in this case, all the cohomology there is comes from conf2, where I can compute it directly, right? There was that little operation of like a little loop where one branch point moves around another, topologically speaking, and sort of nothing new happens in rational cohomology once you've struck 2. So what this tells us, so let's see, I think I have about 4 minutes left in today's talk. So I think I'll say something a little bit in the beginning of my next talk about why one knows this. But let me sort of, because I want to sort of, this is a good moment to sort of make the connection, let me say what this buys us about rational points. So Poincare duality relates HI et al. With H 2n minus I et al. Compact support. And again, this is something you can feel free to ignore if you're not an etalist. So what I want to say is that we end up in the following place. We find that the number of points on this space, what the Grothendieck-Lefschetz formula tells us is that it is q to the n times the sum, the alternating sum of the trace of Frobenius acting on HI et al., not compactly supported, but dual. So this is the Poincare dual version. I probably should have just written this one, actually. For all smooth varieties, this is okay. So this is like some scary, long, alternating sum over et al. Cohomology groups. And sorry, here, X is comp n. But what this fact buys us, that I have over on the left-hand board, the kind of et al. Version of Arnold's theorem, is that this kind of scary-looking long sum actually only has two non-zero terms. So all that higher cohomology is just absent. And so this actually only has two terms. It's q to the n times, okay, the action of the contribution on H naught minus the contribution of Frobenius acting on H1. So that's much simpler. And in fact, and maybe I'll write the duals here. So Frobenius acts trivially on this, so this is 1. And Frobenius acts like q on this H1, so it acts as 1 over q on the dual. So this is 1 over q, and this is the same formula. So let's stand back and look at this for a minute, and then we'll be done for this morning, and then we'll reconvene this afternoon. We have once again recovered the formula for the number of square-free polynomials of degree n over a finite field in what I believe to be the maximally difficult way. I now think I cannot think of a harder proof than this. For this fact, but at the same time as it's difficult, I think it's rather enlightening. Like in some sense we see geometrically why there's no error term. It's because this space literally has no cohomology at all beyond the first two entries. The two terms in this polynomial formula for the number of points, each one has a meaning. One is the contribution of an H0, one is the contribution of H1. And now I can sort of say, and I'll give many examples this afternoon, what I mean by geometric. So the function field version is the version that I proved on the board this morning, and the geometric fact, the geometric version of the square-free polynomial count is the theorem of Arnold. It's the topological fact about the cohomology of configuration space, namely that it has only two non-zero cohomology groups, the rest are zero, the two non-zero ones are one-dimensional. That's sort of recorded on the et al. Side over there. From that geometric fact, we can derive the counting fact sort of for all q at once. And that's kind of the theme, and what I want to spend the second part of this course, the second two lectures doing, is talking about how hopefully, and in some cases with success, we can use that methodology of drawing information from geometry into arithmetic statistics to give proofs of things that do not also have easy proofs. Okay, so I'll see you again this afternoon.